Dear students, we are learning short circuit analysis of distribution system. In the last class we have seen one of the phase variable method where we have seen that we can get fault current for various faults in the distribution system by constructing a Thevenin's equivalent circuit till the short circuit point. However, if the network is very large size, means there are more number of buses in your distribution system, application of this Thevenin's equivalent circuit based method will become very difficult, because it is getting this Thevenin's equivalent circuit itself will be tedious task. In that case, this direct approach based short circuit analysis method will be handy. So, in today's class we will see direct approach based short circuit analysis. So, this direct approach based analysis we have seen in case of load flow method. So, a direct approach we have used for load flow calculations, and we have seen that in load flow calculation we have seen this equation delta V is actually equal to your matrix BC BV multiplied by BI BC into your nodal current. So, I node. So, this particular equations we have solved to get the load flow problem solved. So, in this case voltage difference between actual bus voltage to the source bus is given by this delta V matrix, and in this case we have got these two matrices which are BCBV and BIBC, and these matrices are something like this. We have seen that this BIBC matrix, which basically look like this, for this particular network if you get BIBC matrix, we already seen how to construct this BIBC matrix when we studied the load flow analysis. So, BIBC basically it is bus injection to branch current matrix. So, it will convert your load voltage load currents to branch current. So, these are basically branch current in all the 3 page branches of this particular system, and these are nothing but load currents at each of the nodes. So, these node currents will be converted into branch current using this BIBC matrix. We have seen how to construct that BIBC matrix. Now, for short circuit analysis I am just modifying this BIBC matrix, not exactly modifying, only defining in different way, so that each of these column will be defined separately. So, say this is the first column which is actually corresponding to your node number 2 and phase A. So, that is why I am calling this column as BIBC, since it is corresponding to node 2 and phase A. So, it will be called as BIBC 2, which is subscript, and A is superscript. Exactly similar way, if you say if you considering this particular column here, so this particular column will get multiplied to this particular current. So, this will be called as, this column of BIBC matrix will be BIBC, and it is corresponding to 4th node. So, this 4th will come here, and then this is again corresponding to phase A. So, phase A will come here. So, this column I will call it as a BIBC subscript 4 and superscript A. Like this, if you write for all the columns, you will get matrix which is something like this. So, this column is corresponding to this. So, various columns are corresponding to various columns of this particular matrix, and then we can write it like this. So, these are basically columns which are basically number of unknown nodes. First node is actually known node. So, I am just we are not considering that remaining unknown nodes. So, in this case they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, there are 10 nodes. So, this size of this will be 10 by 1 in this column. So, all these BIBC matrices will be actually 10 by 1 size. So, BIBC we are dividing in terms of columns. So, in generalized way, if you divide general BIBC matrix, it will look like this, which are having many number of nodes here. So, corresponding any ith node, the matrix column matrix of BIBC will be called as this one. So, this is corresponding to ith node and A phase, this is corresponding to ith node and B phase, and this column corresponding to again ith node and C phase. So, this actually nomenclature is given so that we can identify a particular column for the short circuit analysis purpose. Similar way, we have this BCBV matrix, and we have also seen this BCBV matrix during your load flow calculation. So, structure of BCBV matrix will be something like this. We also we are seen how to assemble this matrix, and here this is basically delta V, which gives difference between first node to the corresponding node. So, this gives difference of first node to second node, this gives from first node to third node of A phase, this gives from first node to fourth node of A phase, like this, and these are basically branch currents. So, BCBV, this is V, BCBV matrix basically convert your branch currents to bus voltages. So, this matrix is nothing but branch current to bus voltage matrix. So, these are the branch currents, these are the branch currents, and these are the bus voltage differences. In case of BCBV, I am dividing this matrix as a row. So, this particular row, if I consider of this BCBV matrix, I am calling this row, since it is corresponding to node 2 and A phase, I am calling this row as BCBV 2A. So, this actually corresponding to node 2 A phase. Exactly this way, if you consider this particular row here, it will be called as, this row will be called as BCBV, and it is corresponding to node 3 and B phase. So, it will be 3 and B. Like this, if you write for all the rows of BCBV matrix, they will basically look like this. So, this is corresponding first row, this is corresponding second row, this is corresponding third row, like this it will be corresponding. Since there are 10 nodes, unknown nodes in this particular system, we will be having 10 rows in BCBV matrices. So, BCBV we are dividing into rows, and we are giving corresponding names to BCBV rows, and BIBC we have seen we are converted into columns. So, so BCBV in generalized way, if you write, it will be like this. So, this is corresponding to your ith bus and A phase, this is the row corresponding to again ith bus and B phase, and this any general row, ith row will be actually ith bus is corresponding to C phase. So, it is generalized way of writing your BCBV matrix will be in terms of your row. So, if you write your BIBC matrix and BCBV matrix, we have seen that this is nothing but your delta V, which is equal to BCBV into BIBC, and we have seen that we have converted this BCBV into various rows, and this BIBC we have converted into various columns, and if you do that, we have got this structure. So, BCBV in terms of this rows. So, row size of the row will be actually, if there are n number of unknown nodes, so size of this will be 1 by n unknown nodes, and this will be n by 1. So, each of this component column of BIBC will be n by 1 size, and each of this row of BCBV matrix will be 1 by n size. So, there will be one row and n columns into this matrix, and this is your BIBC as I told you, and this is your I node. So, in short circuit analysis, we are going to use this nomenclature of BCBV and BIBC matrices, and we are going to use it for corresponding fault analysis. Now let's start with common fault which is most occur in our distribution system, that is line to ground fault, where one line get short circuited. So let's say your generalized system is something like this, where this is say ith node, and this is just node before I, this is just node before after I. So this is will be say I minus 1, this is ith node, and this is say I plus 1th node, and this is part of large system. So just I have shown only 3 buses. There may be very large number of buses in the system. Now I need to show B phase also. So this is your B phase, and this is your say C phase, and these are also part of very large system. So I should show dot dot here. And so this is your A phase, B phase, and C phase, and let us say this line to ground fault is occurring on A phase. So if the line to ground fault, if it is occurring on A phase, this will be represented by this structure, and this fault impedance is say ZF, and the fault current which is flowing towards fault is say I post fault F. So this is nothing but your current I, load current in bus I of A phase will be after fault, it will be, so this comma F represent post fault quantity. So post fault current of A phase of ith bus will be given like say this one. Now this fault current is very large as compared to your load currents. So load currents will be negligible as compared to fault currents. In that case, since all other nodes like this node of B phase or node of C phase, they will be serving load currents which are basically negligible. So we can say that B phase current will be almost equal to 0 as compared to a fault current. Similarly, I can say C phase current of ith bus will be also equal to 0. Also all other currents means load currents at I minus 1th bus or any other bus of all the 3 phases, they will be equal to 0 because they are also negligible as compared to your short circuit current in phase A. Therefore, I can write the voltage at this particular bus, ith bus of A phase. So that voltage I can write V I A, which is then post fault, it will be, I am writing it as a voltage of ith bus and 8th phase, and F I am writing for post fault. So if you observe this post fault voltage here, this current is flowing like this. Because of that, the voltage at this point, because of this fault impedance, will be equal to your ZF multiplied by fault current, which is ith bus fault current in phase A. So this will be your voltage, post fault voltage at bus I A phase. So basically we have this BIBC, BCB normal, BIBC and BCBU matrix generalized way, and if you see which entries of this system will change. So here as I told you, all other currents are becoming 0 except the current of phase A, because they will be negligible. So only this quantity will be non-zero. So this quantity will be just fault current in A phase. All other quantities will be equal to 0 in this particular matrix of right hand side. So all the currents will be equal to 0. And on this voltage side, if you see this particular voltage post fault, this voltage will change, and this post fault, this voltage will become equal to this voltage here. So this voltage I can replace it by ZF multiplied by IF. So it is actually ith phase current, ith bus current in phase A. where the fault has basically occurred. So what I am going to do is I am going to replace all these currents by 0 except this current. All other current will be equal to 0, and then there will be post fault voltages at all the buses, and we know this voltage which will be equal to ZF multiplied by fault current in A phase. So if you do this after replacing this voltage here, I have got this term is replaced, and as I told you I am replacing all current to 0 except this current here. All the currents will be negligible. Now if you see this matrix here, and if you see this row, which is basically this row, if you write the equation for this row, it will be just I am taking this equation which is corresponding to this row here. So what will happen is it will be V1A minus ZF into fault current in A phase, which will be equal to it will get multiplied by this row of BCBV matrix. So BCBV of ith bus and 8th phase, and if you observe this part here from here to here of this matrix part, if you see this whole column means this BIBC 2A will get multiplied to 0, this column will get multiplied to this 0, this column will get multiplied to 0, means most of the column, almost all column except the column which is corresponding to this one, which is basically this column, except this column, multiplication of all the columns with respect to the current matrix will be 0. So only this column multiplied by this entry, because this entry will basically only multiply this column. So only multiplication of this column multiplied by this fault current will be non-zero, other automatically will be 0. So so in this column I can easily write from the part which is from here to here, I can just write BI BC IA multiplied by your fault current in A phase. So this is I have done as I told you, since all these columns are getting multiplied to 0 entries. Now if you see this equation is in terms of fault current. So here we are getting this fault current, here also we are getting this fault current here. If you can simplify it, so let us say you can say V1A will be equal to your BC BV IA is one row, BI BC IA this is one column, plus ZF. I can take this I fault current of ith phase, ith bus and 8th phase common out. This will be equal to, okay, it is basically only one entry, so we do not have to write matrix also here. And as I told you, we are basically interested in getting the values of fault current. So values of fault current will be, since it is only one entry, I can just write of A phase will be equal to, we have to take inverse of this. Again this will be only one entry, because as I told you this will be 1 by n matrix, and this will be n by 1 matrix. So if you multiply 1 by n to n by 1, you will get actually 1 by 1 entry, plus this ZF also single term which is fault impedance. So this will be just one complex entry, complex number here. So it will be just, I can say, V1A phase divided by your this matrix which is BC BV IA and BI BC IA plus your ZF, and this I can say V1A of divided by Z SC in case of LG fault. So basically this ZSC in LG fault is given by basically this term here. So, this term basically I can call it into this particular bracket, I can say Z short circuit impedance in case of LG fault. So, if you divide this with respect to V1A, V1A is known because these actually, as I told you, V1A is actually voltages at the first or source bus, where, as I told you, voltages of the source bus are known. So, this is known, and this we are calculating just based on BCBV and BIBC matrices, and as we have seen earlier, this BIBC and BCBV matrices are just based on the line impedances and your topology of your network. We can get these BIBC BCB matrices, and they are not they are generally available with us, and fault impedance value is also available, and from this I can get this fault current for A phase. So, this is your fault current equation which you have got. So, basically what we got in this case, the fault current equation V1A divided by your Z short circuit in case of LG fault, and this Z short circuit in case of LG fault, we have got this matrix here, plus your ZF, and we can easily get this matrix. This is known, so we can calculate your fault current. During the short circuit calculation, we are also interested in calculating post fault voltages. So, let us see how we can calculate this post fault voltages. Again, I am taking that same equation which we have got. So, only in that BIBC and BCB matrix, we have just change this quantity here. As I told you, here the voltage will become ZF multiplied by current which is flowing through this one is fault current in A phase. So, it will be fault current in E phase. So, voltage of this ith bus of Ath phase. So, these are A, B, C phases. So, it will be given by ZF multiplied by the fault current in A phase of ith bus. And here, as I told you, only one entry will be existing because all the other currents will be negligible as compared to this fault currents. So, all the load currents I have considered 0, that I already explained you. So, if you observe this equation here, so if you want to calculate any post fault voltages, so say if you want to calculate post fault voltages of this particular bus, means bus 2 and A phase. So, I can easily write from this particular row equation, it will be V1A minus V2FA, which is actually post fault voltage of bus 2 and A phase, which will be equal to, so this particular row BC BV it should be actually 2 2 2 here. So, it is 2 BCB 2 and A phase, and here as I told you, we already simplified this part of the matrix, and as I told you, all the other column they are getting multiplied with respect to 0. So, they are not contributing anything. So, yes, immediately we can write this total part just multiplication of column which is corresponding to this IF. So, basically corresponding to IF, you are having this column here, which is BIBC IA multiplied by your F, and we can easily write now. So, V post fault voltage of bus 2 A phase will be equal to V1A minus your this part here, that is BC BV of 2A and BI BC IA into your fault current, which we already calculated. So, this fault current is known, only one quantity, and then we can get the post fault voltage of the bus 2. We can also write this equation in terms of all the 3 phase quantities. So, if you are taking all the 3 phase quantities together, say you want to calculate of this particular bus all the 3 phase voltages. So, I can just write it like this. So, similar to earlier slide, I can just directly write it. So, V2F A phase, V2F of B phase, V2F of C phase, post fault voltages of all the 3 buses will be equal to V1, V1B, V1C minus, I need to take all the 3 rows now, BC, BV, 1A, BC, BV, 1B, BC, BV, 1, sorry, here this is 2 actually. So, this is 2 corresponding to second row, because first row is a known row. So, first node is known node. So, we are not considering that, and it will get multiplied, and as you know, the simplification of this part of the matrix, we have seen that it is just BI BC IA multiplied by FA, and this is for say second node. We can generalize way, we can write it like this. So, for all the 3 phases collectively, I can write for any jth bus, I can write Vj. This consists of all the 3 phases, means it will be, this matrix will be basically Vj F A phase, Vj F of B phase, Vj F of C phase, means post fault voltages of jth bus of all the 3 phases. So, instead of writing A, B, C, I am just writing this as a whole 3 phase voltages. Here also, instead of writing A, B, C, I am just writing 3 phase voltages. So, it is just, I need to write as it as V1 minus, this will be again, instead of writing all the 3 phase rows, I can say B, C, B, V of any jth phase, of bus for all the phases, and here this will remain same, BIBC IA, and it will be IIF. So, for any general bus, I can calculate post fault voltages. So, this I just write post fault J comma F. So, any post fault voltages of jth bus will be calculated using this equation, and this fault current is already calculated. So, we can get the voltage post fault voltages, and here we can vary this J from 2, 3 up to n unknown buses, and then only thing is it should this J should not be equal to your ith bus, because ith bus you are not, these equations you are not considering. All other buses except I bus, you can get the all other bus voltages for all the 3 phases using these equations. So, in today's lecture, we have started with direct approach based short circuit analysis. In that case, we have made use of the direct approach based analysis which we have studied in load flow analysis, where we have studied this BIBC and BCV matrices, and in this particular short circuit analysis, we try to make use of those matrices by dividing these matrices in terms of rows and columns. And we have also studied one fault, that is line to ground fault, which is mostly occur in our distribution system. In the next class, we will see few more faults which can be studied using this direct approach based method. Thank you.